Okay. Good afternoon. So, this is the offline session number 11, ATAL FDP program, hybrid microgrid opportunity and challenges for renewable energy resources. I am Dr. Shivam, Assistant Professor of Electrical Department, co-coordinator of the ATAL FDP program. Heartily welcome Chief Guest of the day, Professor Barjeev Tyagi sir. He is a professor in Electrical Department, IIT Roorkee. Coordinator of the ATAL FDP, Professor Ratna Dahiya. Coordinator of the School of Renewable Energy and Efficiency, Professor of Electrical Department, NIT Kurukshetra, and faculty members and participants of the event. The primary objectives of the ATAL FDP is to provide a national forum to the faculty and research scholars to share the basic knowledge with an objectives of understanding the concepts, aspects of penetration of renewable energy sources, electric vehicles, and with hybrid microgrid operation. Now, I would like to address of today's session, second session, a speaker, Professor Barjeev Tyagi sir. Currently, he is a professor in Electrical Department, IIT Roorkee. So he did PhD, MTech, and B from IIT Roorkee in 2006, 2000 and 1987. He has guided more than 50 PhD and more than 50 MTech students. He is IEEE senior membership, and sir has also honored Best Paper Award. Sir has guided more than 10 major projects, DST projects already have completed. So now sir has research area in microgrid, a smart grid, a small signal stability analysis, control of wide area power system, a stability analysis and controller design, wide area system monitoring and control, PMU placement in transmission and active distribution system, power system operation and control, power system deregulation, voltage and frequency control, microgrid planning, operation and control, integration of renewable energy sources with optimization. In that way, I would like to welcome sir for this session. Please, sir.
यहीं पे बैठ के करना, रिकॉर्डिंग में रहेगा ना, कहीं पे भी उधर। Let's start. Okay. Good afternoon, everyone. So, as Shivam introduced me a lot, I'm faculty in electrical engineering, IIT Roorkee. And today's topic of discussion is the microgrid modeling and control. I think a lot of things already have been discussed. Okay. So we will try to keep our session more interactive. So what is a microgrid? So this is the given definition, although you cannot say that many standards have been set up till date. But in general, we accept the definition of this as a microgrid, which is a controlled small scale power system consisting of the small scale emerging generators, loads, energy storage element, and control unit that can be operated in an islanded or grid connected mode, capable of supplying a local area such as the suburbs area, industry, any commercial area with electric power and heat with improved power quality to the consumer's premises. So what we can call a microgrid? It may be from very mini to micro level. Even I can make this room as a microgrid. If I can provide the sufficient source which can cater the load of this room, so I can treat this room as my microgrid, which may be connected to the main grid, or it can work in islanded mode. Where the two main things, whether it is connected to the main grid or islanded. What is the difference between these two? In grid connected mode, we later will discuss, it can absorb or supply the electric power. It can take power from the grid, and whenever there is excess, it can also supply to the grid. In islanded mode, it is disconnected from the grid and it will have the sufficient power to cater the load connected in that particular microgrid. To cater the load, so even the load management we can also place as an element of the microgrid. The objective associated with microgrid, why we want this? The improvement in the power supply reliability, which is a very common thing in India. Whenever we will feel we can cut off the load, there may be the different region by which this load shedding is being done. That may be the purely technical or the shortage of the supply. Even then we can go for the cutoff of the supply. To alleviate the environmental impact, which is again the very important factor. If we are talking about with the international carbon emission standards, so we have to reduce the carbon footprint, we have to improve the environment, and majorly we go for the renewable sources. As we know, the renewable sources, although we are connecting with the main transmission system, in India itself, we will have the plant as big as more than 200 megawatts. And in the one example, we are seeing if we will combine the one particular area in the Rajasthan, that power is going beyond the thousands of the megawatt, which is purely developed by the solar. So in such a big case, we are connecting these renewables with the main transmission system. But mostly, like the government is promoting to just to have the rooftop solar. So where you will connect these solars? They are normally coming into the distribution side, reducing the load on the main grid, and simultaneously each solar installation is reducing the footprint even by the 0.00001%. So directly it is impacting the environment. Improvement in the stability and efficiency of the system. So the broadly available, what is the main reason for the instability in power system? Anyone? If you know the definition of the stability, it's a big definition. We can have the frequency stability, rotor angle stability, and voltage stability. If you will just think about the rotor angle, which is the more crucial, divided into the small scale and your transient stability. So a small deviation in the load is very frequent in the normal operation of a power system. Because suddenly we are switching on, switching off, it's a very random process. Even we will switch off the 5 ACs here or the 5 heater in one room. So that is directly going to impact your system. Now, once we will try to cater all this load locally. So ultimately what was happening? This whole impact was appearing on the generating plants. And whenever there is a inter-area oscillations which are finally leading to the instability, they are going to be reduced. Because locally now we have created the sources and the load which are supplying here. So the major problem, the stability which are coming into the power system, that probability is reduced. But on the other hand, if we will are connecting like a microgrid, it may have its own stability issues, but that are not going to impact the bigger generators where it is a more crucial. So that's why we say the improvement in the stability. Efficiency, because we are reducing the chances of the power cutoff. So naturally the efficiency of the system is improving. Sorry. Just a minute. Ensure diversity of the energy supply, because we are using our power supply can have reached to the remote areas. This is the another big advantage of these microgrids. Even now, today's India itself, there are the many areas where we don't have the facility of the transmission line. They are based on the requirement of the area. A small setup can be created, which can cater the electricity need of that particular area. Cost reduction in the electric plant. Say if we will compare the per unit cost, nowadays it may be higher than the normal coal plant. But the another advantage is the big land area which is covered by the coal plant, that is being reduced. So if not now, but in future, we can see the reduction in the cost also of electricity. Motivation behind creating the microgrid is the development of the renewable energy sources in the fast pace. In the last 2-3 decades, a number of energy sources other than the conventional, now we are seeing in the form of the solar, wind, which are very common. Very fast emerging is the hydrogen, or can say the fuel cell, which is a very big source of the energy is going in the next few years. And all form of the energy like the tidal and the other, they are being utilized as a renewable source. One more important is the small hydro. In the big hydro plant, you require a lot of big dams and other things. But in the small hydro, the flow of the any canal or the river is being utilized to generate the electricity. So they all fall in the different form of the renewable energy resources. And this energy, if we are utilizing you locally, that is the more efficient way. Environmental concern, increasing power injection in the renewable energy, development of the distributed energy resources, and can supply power to the remote locations, which we have discussed. So based on this, the more attention being paid to the microgrid, so that the small grid can be developed. This we can take is the basic structure of a microgrid. What we are seeing is this side is my grid, the basic grid. This PCC is called the point of common coupling. With this given switch, we can connect it with the main grid, or we can disconnect with the main grid by using this circuit breaker. From the low voltage side, say suppose my main grid is coming from the 220 kilovolt, and here we are going up to the 33 to 11 kilovolt, mostly in case of the microgrid. So the different type of the sources can be integrated with this to cater the local loads which are available in this particular area. They may be like the wind turbine, solar, flywheel, all kind of this sources can be utilized depending upon the location and the availability of the source in that particular area. But mostly in all kind of the for all kind of the sources, we require the power electronic interface. In the different ways, different type of the converters, inverters, which are required to connect it with the consumer. Like my solar give me the output of the solar panel is DC in nature and at a given particular voltage. So this interface devices will convert the voltage level up to the required one, and also the nature of the supply which we are using, whether it is DC in nature, AC in nature, mixed in nature. So with the invention of this power electronic interface, we can plug and play with the sources which are available to us. In the wind is generating in the variable frequency power, which are finally converted into the AC or DC. So this is the basic structure. Whenever this switch is closed, the circuit breaker is closed, we call the operation is in the grid connected mode. So if there is a lack of power, it can draw power from the main grid, and whenever there is a power excess power, it can supply to the main grid. But when circuit breaker is open, then the whole system work in the islanded mode, which we call the islanded mode. It is not connected with the main grid. So whatever be the sources are here, it has to supply the load with the help of the given sources. If the load is more than the generated power, then normally we go for the load management system. Then we divide the load into the critical load and the non-critical loads, and we take the shutdown of the non-critical load while the critical load are being supplied. So that all is the part of your this microgrid. One more point here, when we are working in the islanded mode, then we will face the more of the control problem. When it is in the grid connected mode, on the low voltage side, normally all the frequency changes and the other thing will be taken care by the main grid. So majority of the control problem appear when the microgrid is working in the islanded mode. Challenges in developing countries like India, they will have the costly installation and their payback period is very high. Now, although it is given the 15 years, but in case of the solar, the recent studies which we have done in our project, that is giving the payback in the 6 years. But still, if you have the big wind plants and the other, their payback period is still to be very high. Shortage of the skilled hand. Now the work is on to develop the skill in this area. Production and the operational issues. These issues are coming just because of the most of the time we are placing these sources in the distribution system. What is the impact on the system? Anyone can comment? What is the impact of the renewable in distribution system? Peak load? It can reduce the peak load, that's fine. But what is the operational impact and the production point of view, if you will see? Say the conventional distribution system was, we are getting from the substation the power we are getting, and from that particular substation, like the 33 kV, from 33 kV onward, you are supplying the power. So your current is flowing only in the one direction. Because other side is only the load, no other source was there. Then the studies like the power flow studies, protection studies, overcurrent. So there are no directional component. But as you are introducing the renewables at the different ends of your distribution system, now what they are doing, they are injecting the power. Although this power they are giving to local load, but once we will say it can also supply the grid. This means they are giving the directional component to the current. Now, the current can flow in any direction. So because of this, these issues are appearing in the system. So, and mainly the production, because the directional component has a very big impact in the production of the power system. And similarly, the operational issue, which was the one direction, now it may be in both the direction. Although in a small portion of the network, but there may be. So that's why nowadays we are thinking to place the PMU in the distribution system. The major advantage of the PMU is they can also measure the angle. What is the magnitude and the angle of my phasor quantity, voltage or current? In the distribution system, the phasor was not so important because you are moving in the one direction only. If it is in the both the ways, then of course the measuring device is also become important in the distribution system itself. So this is another challenge. No specific standards and the regulations are still available in the in microgrid. Even the distribution PMUs which we are being used, many of the application you can find, they are still don't have any standard. The PMUs used in transmission system, they already have been standardized. You will find the IEEE standard for this, what to follow when installing this, but in distribution, still no standard is there. Low take-up, lax payment mechanism, even what should be the market? Now electricity, if we are using as a commodity, and a lot of work has been done in the restructured power system, or what you call the deregulation, how to basically a generating plant will get the payment. How will basically cost the electricity. But in case of the renewable, it is so intermittent. Still, how to make payment to these basically operators, those who are developing these plants. So there is no standard mechanism. Depending upon the government to government, state to state, their payment methodology changing. Like in the house, we will have the reverse metering in some places. So reverse metering is how much you are taking from the grid, how much you are feeding to the grid. Based on that, your electricity will be calculated. But the few states are following it. In India itself, few are not following. Capacity building, promotion, and the development of energy. So still, like we said, the research is on to get more and more renewable sources. Few have been established, like your solar and wind, hydrogen, a lot of work is being done. So in future, we can see the more application by the hydrogen itself. Requirement of the servicing companies for local program implementation. This is another big problem that is particularly appearing in the institutes. We are working on a very big projects. The crores of rupees are being funded by the government and the other sources to develop such facilities. Till your project is on, everything is fine. Although we say the operational cost is, there is no operational cost in the renewable. But still there is a lot of maintenance cost. Even in case of the solar, you require the very frequent cleaning of the panels to improve the efficiency. And that this cleaning itself is a very big task. If you have the megawatt plant, so in that case, you can see how much cost is required to clean up the panel itself, if once in a month. So that's why the servicing companies are required in this area. Sustainable revenue business model requirement is there. Like we said, a lot of research is being done. Even now, India's solar case, solar and the wind are being implemented. But still the other renewable sources is still to be explored and to be introduced into the electricity markets. That kind of the business model is still lacking in this area. And this is a very important issue, the inherent intermittent nature of renewable energy sources. So that will depend upon your In India, particularly in this range, solar is very good. But कहते हैं कि मौसम के मिजाज के साथ इन सब का मिजाज अपने आप बदलता है. A lot of intermittence. Suddenly the cloud will come, the power, your plant which was giving you the working at the 80%, now suddenly reduced to the 20-30%. So suddenly a lack of power is appearing in this. So such issues are basically what is happening in this case. Suddenly you have reduced the generation. Load is still there. So a lot of issues can appear. And these to be, of course, answered here. So very quickly we can see the power scenarios of India. So our target was the 175 gigawatt, and still we already have been achieved. The share of the solar, wind and biomass, I think a lot of already have been discussed in this. This is the international scenario. In India, we are heading in the solar, but still lack in the wind. Small hydro is also a very big challenge, and the most of the power is being utilized in India. This is the state-wise scenario for the solar, which is given here. So the microgrid benefit, if we will see, we will look them from the utility point of view, from consumer point of view, and for government point of view. For utility grid, it is reducing the feeder congestion and managing the peak load demand, as one of the participants was just still discussing. And as we said, these microgrids are local in nature. Suppose NIT Kurukshetra itself, I don't know what is the status here. You have solar 1 megawatt. So 1 megawatt solar is already here. Suppose it is not there, so this power is coming. What is the peak consumption here? Up to 5 megawatt. And the variation will be, in that case, will be from near about 2 megawatt to 3.5 megawatt. This will be the local all day variation. If the 5 megawatt is the peak capacity, then this much is appearing. If solar is not there, the whole power has to come from the network. Suppose your 1 megawatt installed capacity is there, if not the 1 megawatt, but at least 500 kilowatt or 600 kilowatt, for at least the 6 hours you are getting. So this much power you are locally supplying. Even you are feeding to the grid, grid is still feeding back to your NIT. So from where this congestion is removed, that is removed from your distribution as well as on the transmission system. And in such a unit you will have spread out throughout the system. So we can very efficiently manage the congestion. Naturally, if the current level is reducing, your transmission and distribution losses are reducing. Ensuring power to the critical load during the grid fault or blackouts. So the technical shortage of the electricity, that is some line has been broken. So naturally in that area you cannot supply. But if you have the microgrid, you can ensure the supply to your critical loads. And the better demand and the supply mesh due to decentralized power system. So naturally, all this will improve the efficiency of your system. From consumer point of view, better backup with reliable and the better quality of power, improve life cycle of your appliances. Consumer becomes prosumers. I think a lot of discussion already have been done. What we call the prosumers? Producer plus customer. Like we said, I have my rooftop solar, but every time I'm not using it. Both husband and wife are working, they have out from the home, room is locked, but still your solar is giving you the power. And that power is being fed to into the grid. And even if you are at the reverse metering, so whenever you require power, you are taking from the grid. When it is not required, you are feeding to the grid. So you are producing and supplying to the grid. So consumers are prosumers. You are producing as well as consuming. Remote area consumer can benefit from the standalone microgrid. Some hilltop is there, no transmission line, and still you can supply electricity to these consumers. And the big benefit with the government, the use of renewable sources will help government ease environment concern. The PM can take a step to announce, okay, up to this, we will reduce our carbon footprint. So internationally, a lot of pressure is on each country. So you have to go to the renewable. It will lead to job creation. Naturally, if the more installations, more jobs. Reduce people migration will cause the better human development index. So from utility, which are basically your supplier, we are the consumers, and the government, which is investing money into this. Challenges of the renewable energy integration. Few of them we already have been discussed: balancing supply and demand during generation, scarcity and surplus situation, which is very common with the renewable sources. Suddenly, you have the access of this. You don't have the load, access of the power. Where this power will go? Suppose you are in a standalone system. The solar is generating power, 10 kilowatt. Your load is only 2 kilowatt. What to do with the 8 kilowatt? If you don't have storage, then either you will store even the store is full. So sometimes you have to create the dump load. You have to waste this power. Otherwise, what will happen? MPP we will discuss. That doesn't matter. MPP will be required when the load is more than the supply. Then it is required whether you are working at the maximum power point or not. If you don't have that much of the load, this will give rise. So what will happen in that case? In the light load condition, receiving end voltage will become the higher than the sending end voltage. Sometimes you will get a very high voltage at that equipment, which can damage. This we have experienced in our Roorkee. On the solar, what they have done in a project, on each department, we have the current 2.5 to 3 megawatt. solar installation. They have been installed on each and every department. And these solars are basically supplying to the grid. They are connected to the grid and we are taking supply from the grid. There's some kind of the reverse metering. If your supply is off, then inverter is off. But if the supply is there and load is being supplied, so what happened in the daytime? Normally the load is very high in educational institute itself. But in the off time, when the offices are off, your all ACs are, office ACs are off. In the hostel, no AC is provided. So there's a simple load is there. So what happens? Then the voltage rises to very high. And many of the equipment has burned. So that is the balancing of this supply. Sorry. This balancing of the demand during the generation is scarcity and the surplus situation. To handle this situation is also a very critical issue in case of the renewable. Voltage management due to heavy reactive power drawn by renewable generators, particularly the wind, where you use the DFIG type generators, the induction generators, which require a very heavy reactive power. Due to intermittent and the unpredictable nature of the renewable energy resources, power management between various resources, regulation of the voltage, frequency, they are still the challenge. The few of them we will discuss in our discussion. And due to the intermittent nature of RA resources, they present a problem to the optimal sizing of the energy storage devices. Still we are using, but how much? So normally the solar and the other which you are installed, that we will install with the storage, battery storage. But how much battery storage you will provide? If I have for example, I have the 100 kilowatt solar plant. So should I provide the 100 kilowatt battery? That is not a feasible solution. Mostly we go up to the 30%. So that's why if you will go for the planning, then the optimal sizing of the energy storage devices is still a big issue. I think those are the PhD, you are doing PhD, they will be facing this problem. So microgrid characteristics, particularly we will have the flexibility, interactivity, compatibility and economy. Flexibility, microgrid, mainly all these properties are emerged due to the operation of the microgrid in the islanded as well as in the grid connected mode. So the grid connected mode acts as the normal operation in which model the system can either absorb power or can supply power to the grid. Interactivity, operating in the isolated network, state can not only shorten the consumer's power outage time, but also help reboot the bulk grid. Have you heard the cold load pickup? Problem is what? Whenever you will face the blackout, 2-3 blackout you already have been seen. 2012, when there is no power in the entire grid, how to boot your system? That is called the cold load pickup. So you cannot basically switch on all the generators randomly. It's a very stepwise process. You basically lighten up first the plant, because plant itself will need the energy. The most of our generators are the synchronous generator. And in the synchronous generator, we know what is the field? Field is the DC. So you require the DC. So sometimes you use a complete backup to restart the plant. So rebooting the plant itself is a major problem. With the help of microgrid or the small installation like this, what we can do, we can light up the small portion here. Then say not the whole and Kurukshetra, the small, like the departments are basically given the supply, which you already have with you. So that all will help in rebooting the system. In compatibility, microgrid is the most effective way to achieve the connections of distributed energy. So in a conventional system, we will have the normally my sources are concentrated at a particular point. And from with a long transmission, we are basically evacuating the power from one point to the another. The advantage is the distributed energy. Locally, we are supplying the load. So that is the most effective. Microgrid is creating that. All distributed resources we are using at one point and make it independent from the main grid. Microgrid access to large amount of the renewable energy, which means we can distribute the output of the different micro source optimally. So whatever the sources we have, we can use them optimally to get basically to supply the need of our all consumers. If you will see the microgrid architecture, the first we have seen, we have the main grid and which is connected with the different renewable sources. Further, we can divide them into the three main categories. The first we call the AC grid, AC microgrid, in which all the renewable sources which we will have, they are connected with a AC bus. Here we start with the utility with point of common coupling. They are connected to this AC bus. So we can say this is the transformer which is converting this from say the some high voltage to the low voltage. Suppose my bus is of the 11 or 33 kilovolt. We can have the PV, battery, micro turbines, EV, they all basically are generating electricity in case of the DC. Their output is DC. This DC output we have to convert into the AC output. So at the different level, we can have the different buses depending upon the concentration of that point, that particular sources. And dividing our load into the same like your critical load and the non-critical loads. So a lot of converters are being used which are converting the suitable form of electricity which is AC in this nature. But the whole load is being supplied by the AC. Sometimes like here we can see the EV is supplying the some local load. Here this can supply the some local load. Here they can supply the local load. And overall is connected with the main grid which is also supplying this load. Because they are intermittent in nature. If you will have the shortage, then the actual power we are taking from this utility grid. Whenever this PCC is the circuit breaker connected to this is off, then this will work in the islanded mode. Then the complete operation or the all load is supplying as the AC load. That complete grid we are calling as a AC grid. Then we will have the DC microgrid. So here we will have all my generation which is connected to a DC bus. So what we are doing, even the utility, the AC we are converting into the DC and connected to this DC bus. Whatever be my sources like the wind and the power, battery, they all use DC to DC converter. Sorry, the PV and battery, DC to DC converter to bring the voltage level of this DC bus. In case of the wind, normally we use the dual converter. We are converting AC, which is of the variable frequency, into the DC. From DC again we are converting into the AC, like we are doing here. If we have a wind turbine, we use the dual converter here. One is converting AC into DC, then this DC we are converting into AC. So here this conversion is not required. We can convert this AC directly at the same voltage level which we are converting. We use this bus. So here we will have the DC bus. My load may be the DC load which can directly be used, or the AC load where we convert DC into AC. Even in the DC we can have the different voltages. Now a lot of bulb fans which are available in the market, they are of the different voltages. 12 volt, 24 volt, 48 volt. But normally in DC distribution, we try to keep this voltage very high. Suppose we have a 48 volt load here, DC load, and the 48 volt bus voltage, we can connect it directly. But it will depend how long it is connected. In case of the DC, because the current has to flow, the voltage drop will take place very rapidly. Even if you will have your resistance of the wire, connecting wire, simultaneously you will have the joints. If it is 0.01, you have the 48 volt, 10 ampere is going. So 1 to 2 volt drop can be there, which maybe can affect your appliance. So try to keep the voltage of the bus high, and we will convert at the where we are using the power. Suppose I have put a lamp of 12 volt. My voltage line is say the 500 volt. So I will bring up to the fan 500 volt, and to give the fan I will use a converter which is converting 500 volt to 12 volt. So the buck converter I will use and convert this voltage into the 5 volt. So current in my appliance will be more, but the current which is in the wire, that will be very less. So that is my DC microgrid. And like your course, we will have the hybrid microgrid, in which we will have the both AC and DC. So we have the two feeders. One is the AC feeder, other is the DC feeder. Here we will have the utility with the PCC connected with this AC bus. In DC case, we are converting this AC into the DC and connected with this DC feeder. In AC feeder, if the voltage level is same, so we can directly connect it. Otherwise, we can use the transformer to change its voltage level. So wherever you will have and the source is also distributed here. In case of the DC, we are using this structure. In case of the AC, we are using the AC grid structure, and both the loads are catered separately. AC by the AC bus, DC by the DC load by the DC bus. So by this, if you will basically compare all the three systems, so we will get the best efficiency in the hybrid case. Like you can see, we can generate this system, but a lot of power electronics is involved. So if you have any doubt, any questions, then please keep discussing. So we have the three types of the architecture: AC, DC, and the hybrid. This hybrid microgrid, in our one project we have developed, and this is Karib 200 kilowatt microgrid is in operation in the Dayalbagh, Agra. It was a joint project between IIT Roorkee and Dayalbagh, in which this 200 kilowatt microgrid is developed, which require near about the 2 acres of the land. And objective was, basically I have not covered in this discussion, so that's why I'm just giving you the information. There we use the 200 kilowatt solar panel, which are installed at a 16 feet height. So we use a tower. Each tower will have the 10 kilowatt. So near about the 20 tower we have installed in like approximately 2 acre area. The advantage here was the just two, so we can have we can cultivate the land as well as can have the solar power, both. And that was the hybrid microgrid. There all the lighting has been done using the DC lighting and the fan. Even the chiller is developed, cold storage, which is also hybrid in nature. Sorry, the DC in nature. One more question. What you call these ACs? Inverter AC means what? Sinusoidal current. Why we calling the inverter AC? Which normally reduce your electricity consumption. Anybody? Not sinusoidal. What is the concept behind this? कैसे 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 वर्क कैसे करेगा? What will be the steps? Pulse width modulation. वो तो इन्वर्टर का एक्शन. We already have the AC. Then why are you using the inverter? Inverter normally used with the DC. What we are doing, we are getting the AC, converting into the DC, and then again inverting. Why?
Constant voltage.
Voltage is constant. We use a stabilizer, voltage is constant. Changing frequency. Right.
This is a variable speed in AC.
Variable speed AC.
We set the temperature, we achieve the temperature with the AC. AC compressor will be cut off. But in inverter AC, compressor will not be cut off.
Very good. So initially what we are doing, we are using the switch on and the switch off concept. We are directly using, even my compressor is AC in nature. We can have the DC compressor also, but our compressor is AC in nature. Initially, we are running the compressor, achieving the temperature, and it is cut off. So whenever you switch on and switch off the AC, it will draw a very large amount of the current. So sometimes you can see, I don't know whether you have experience or not, if you have 2-3 ACs and they simultaneously will be on and off, so a very large amount of the current will come and even your MCB is tripping. So your compressor was on or off. Like in your geysers, your thermostat will work. But in inverter AC, what they are doing? For AC motor, the best way to control the speed is V/F control. So now we are using the on and off controller. First, now we are using the PID controller. So what you are doing, whenever the temperature is increasing, your compressor speed will control. That will come down. That will draw the very small amount of the current. When it will reach to the temperature maintained, so you can feel your AC is off, your compressor is running, but a very, very low speed. If you have observed the fan speed, sometimes try to observe throughout the time, 7 or 8 hours. अभी तो सर्दी है, जब गर्मी आएगी तब देखिएगा. So your compressor speed, the speed of the fan, that keep on fluctuating. And it is observed that you can save the near about the 50% energy. So what we are doing, we are having the AC converting into the DC, and from DC again you are inverting. Because now this inversion, you have the flexibility of the V/F control. So here a lot of work can be done. When you will have the DC and you have to supply the AC load like your chiller load, which we call the cold storage. Again, a compressor is required, refrigerator, AC. So can we develop the compressor? We can use the DC directly because the one stage of the conversion is off now, which we are converting the AC into DC. Conversion loss, equipment cost, everything will be reduced. So that is the another application which we can have. So these are a few merits and the demerits. We already have discussed. 2 modes, grid connected mode and the islanded mode. So grid connected or on grid mode, islanded, standalone, off grid mode, we already have discussed. If any question, then please discuss. In grid connected mode, microgrid is connected to the utility grid at the point of common coupling. Amount of P and Q to be injected by DG is decided by MGCC. MGCC, you can recall the switch which is connected with your PCC. Converters operates in PQ mode and the utility grid determines the voltage and the frequency reference. Say, once you have to control anything, what is required? The reference input. So when your system is the grid connected mode, so all the control operation, you will take the reference of frequency and the voltage from the grid voltage. When it is in the islanded mode, then these references you have to generate. In islanded mode, microgrid work autonomously, converter acting converter, now they will be the voltage source. In case of the grid connected mode, they are normally the current source inverter. I'm not the man of the power electronics, but I think that tomorrow they will discuss about the power electronics. So grid connected, normally we have the current source inverter because you are injecting the power. The power injection will normally is done in the form of the current. So again, from technical point of view, it's not so simple. You will connect it. So that is the current source inverter. But once you are in the islanded mode, you have to keep the voltage constant. Because your all operation is done at a given voltage. So you normally use your voltage source inverter. Operating set points are obtained by centralized or the decentralized control. Because now here all the set points are basically governed by the grid. But here these set points you have to generate. What voltage and the frequency you need for your system in islanded mode. So to implement all this is the all journal, then what is required? That is the microgrid modeling. So once we will start analyzing any engineering system, our first step is to model the system. Get the mathematical model of that particular system and then use your analysis, control and everything. So the microgrid modeling technique, we divide into the 4 categories: component wise, single entity lump model, stochastic model and the dynamic equivalence. Component wise means there is a lot of component. You have the supply, you have the converters, you have the transmission line, you have the loads. They all will has to be modeled. So this component wise modeling is normally being done either in the transfer function form or state space model. And how these components are connected, they all are aggregated. And then this aggregated model now comes to be a very large state model. This state can go, depending upon the application, up to your 20 state, 40 states, how many sources you are using, so this aggregated model will be very large. That is the further to reduce it. Now single entity in the lump model, all we have converted into the one entity and then model the system. So the two will basically reach to a very large amount of the large size of the system. Then to design, control and the other model order reduction technique can be utilized. So stochastic modeling and the dynamic equivalence which you will have here, nothing but whatever we are doing here, we will consider the noise in each modeling. And in that case, when we will use the stochastic model or the noising model, then in place of measuring the state, we will try to estimate the states by using like the Kalman filter, unknown Kalman filter, different type of the analysis. Dynamic equivalence means whatever we have obtained by this, dynamically how we can have the equivalent system with this. We can use the Prony analysis, coherence principle, system identification, characteristic model or ANN model. We can treat the whole system as a black box and then can estimate we can identify the system using the different approaches. So now very quickly, I think you already have been discussed all this thing. This is the solar cell model. How you will basically model a solar panel. What is a panel? What we call a solar panel? Anyone? A collection of the solar cells will make a panel. The solar cell is fixed. Now, how you are arranging the solar cell in a panel? You can connect them in series or in parallel. So they will decide the panel specifications. Anybody can give what is the solar panel specifications? How will decide the solar panel? You want to install a solar system in your house. You all are the electrical engineer. How to develop your solar system? What is the rating which is given? VOC, ISC, short circuit, power. There are three major ratings. Others are also given, which you call the factory specifications, which is there. So they will decide a panel. Like say what is the best panel available here? Maximum capacity is 100 watt. Not exactly 100 watt. 100 watt, OCC 36 volt. Similarly, the current rating, depending on the 100 watt. In which this is the model of a solar cell. So these cells will have a certain voltage V and the current carrying capacity, where I is given by this equation. So what is the panel you have to create? These cells you have to connect in series and then in parallel, just to build up the current carrying capacity, which is giving you the power, and the series connection giving you the voltage. How much voltage you can apply. Now from one panel, which is of the 100 watt, now you require say a 5 kilowatt solar system at 120 volt. So again, now you have to decide the panel. How many panels will be required and how these panels will be connected with each other to get the desired voltage and the desired power. So that is the model of a solar cell. This is the solar, you have the panel, then you will have a DC-DC chopper and the inverter where you are getting the AC. So what will be my solar panel or say the solar system? That we are deciding based on the solar cell and the panel. So you are deciding what will be your output voltage, what is the power it can supply. This DC-DC chopper is converting what is the voltage level here to inverter input voltage level. At the inverter, we will try to keep this voltage constant. Now here at this end, this voltage that will depend upon what is the solar irradiations are here. Now here comes the concept of the MPPT, maximum power point tracking. So whatever we will discuss in after a few more slides. So you will try to extract the maximum power from this. So you have to basically not operate at a constant voltage. So this voltage keep on varying, but you will try to keep this voltage constant. So that's why you use this DC to DC converter, which object is to draw the maximum power and to keep this voltage constant. And then you will have the inverter with a given frequency and the voltage, which give you the output. And simple KVL and the KCL can be applied to develop these equations. Normally, to develop this inverter equation, we use the DQ reference. I think all are familiar with the DQ reference frame. In the DQ reference frame, all these equations are written. They are very standard equations. In the literature, you will get a lot of things just to develop all these equations. So my first state space model, a simple AC system with inverter, will appears to be a 4-state model, which is written in the form of the x dot equal to AX plus B U1, B2, U2. U1, my inputs are the D, delta MA, and this is the VD, VQ. This D delta MA is coming from where? That is from DC-DC chopper, D delta, and IDIQ that is coming out from my inverter, VD and the VQ. These are the ABCD matrix which from this is developed. So this model can be used to get the model of this solar PV with inverter model. So this is the modeling of a wind turbine. Here a doubly fed induction generator is modeling is given, which is very common to use. Anybody can explain what is the doubly fed induction generator? Any idea? Power can be extracted from both rotor side and stator side. So here you require a prime mover which is rotating. So your rotor and the stator both are 3-phase winding. But on the rotor side, it can supply the power as well as it can absorb the power. That will depend. But from stator side, this is supplying the power. Now, as we say, the induction motor can run below and above the synchronous speed. If it is above the synchronous speed, say in both the case, say what you will have? You have the 3-phase winding here, 3-phase winding here. So once it is above the speed, both are supplying the power. So what this side is doing, you will have, say here the 3-phase power directly given to the grid. But on the rotor side, you will have the AC power, which is of the variable frequency, converting into the DC. DC further, you are inverting and giving to the grid. So whenever you are below the rate, synchronous speed, it will draw power from here. When it is above the synchronous speed, it will give power from here. So that is the advantage of the DFIG. In both the cases, it can supply the reactive power. Here the detail of this generators are given, the different structure. And again, the 5th order model of the DFIG is given by these equations. So for the solar We have the 4-state model. For DFIG, we will have the 5-state model. Models are not giving, these are a simple KVL, KCL. Equations are here. A lot of literature is available. You can directly use them if required. Another important parameter is your battery model. The battery we use either the series RC circuit or the parallel RC circuit. This is the series RC model. VOC is given in term of the SOC. And this is the parallel battery model. And this battery model will also come of the 4-state model. So 4 plus 5. When you will have a combined system, so most of the time this combined system we will basically represent by the converter, RC filter and the load, which is connected at this PCC point of view. So all whatever be the sources you will have, that basically will be taken by this P. This is the another form of the modeling of the microgrid. So whenever, say, in most of the literature, you will find once they are discussing the modeling in the microgrid modeling, they normally don't consider the source. In the place of the source, they will show only a constant DC source. What the constant DC source is? Either the output of this DFIG or the output of this solar system. So this they assume, and they will used as the microgrid inverter, and the whole source is considered at this particular point, which is of the DC source. That is basically considered at this point. So they are using this DC source converter. The filter is used just to whatever be, if there are harmonics and the other things are there, just to avoid them. And then they have transformer just for the suitable voltage level and whatever be your load. You can model your load, either the dynamic load or the static load. Whatever be the voltages is here, that is used to basically use the controller, to develop this controller. So what they are saying, the PWM, once we are discussing about what should be the inverter AC. Inverter AC means this DC you have, and then now you are inverting. So this inverter firing circuit is normally use the PWM, pulse width modulation, just to generate the firing pulses for the inverter. So that all is basically your power electronics, which you have to develop. Once you will club all these different sources, they may be so similar or the different, then in aggregation, you can have such kind of the equations or the models. And these model for two sources is going up to the 14 state. And this 14 state model with these parameters which are given, you can basically make the eigenvalue analysis of this, which can be utilized to study your stability, controller design, many factors. So here you will find these three critical poles, which are very near to your J omega axis. Although the overall system is stable, but a small disturbance can create the instability in the system. So that is my purpose here is just to develop this. Although naturally all these things cannot be studied in the one class. So all literature is available. You can find this. Say how to basically develop this model or battery model, DFIG model, solar model. These all are the known things now. Separately, you know this. But once you will convert them into the grid. So as an example, we have taken a two-source system. You have the one source here, one source here. They are connected through this transmission line, distribution line. So what actually will be the impact of this system? So that is only the one example, but in your case, you can have the different locations, more than this. So what, as a researcher, you know the separate model is known, but once you will club, that is your new thing. How to get this aggregated model and how to analyze this aggregated model. Like once you will have this model, a very small analysis, the eigenvalue analysis is shown here, which is further then used to develop getting the stability margins, get the controller, how to design the PWM, what to design the PI controller for your converter, so that you can improve the stability margin as well as the can design the controller for your own given system. Because the microgrid structure is not a constant. But like we said, most of the time, up to the DC voltage, you are doing as a separate thing. And the overall microgrid, after this constant DC, your microgrid structure will start, architecture will start. And here you have to basically develop your controller and the other things. Hope I'm clear. So they are the few objectives for the microgrid controller. Plug and play feature when integrating new DG into microgrid. Say you have your own system here in NIT. Say you have installed, like say 1 megawatt is installed. Suppose further now the biomass is improving, you can have a project by which suppose you are collecting the waste of your all the masses and convert this waste into energy using the biogas, biogenerators and other thing, and now integrate this with your system. So what basically you require? You have to develop your technology in such a way that like you will put a source and can use any of the computer here. Similarly, you can put a plug source, integrate with the system and directly feed the say 20 kilowatt into the system. So that is the plug and play feature when integrating with the new DG into the microgrid. This plug and play is nothing but the type of the controller you have to design. So these controller you are designing to integrate the new DG with the microgrid. Controlling the DG power flow, dynamic load sharing in islanded mode. This is again a very important issue in microgrid. You have the different sources, how to share the power. Suppose you have the two batteries. Each is can supply, let's say, the 1 kilowatt. You have a a load of 0.75 kilowatt. Sorry, 112, say 1.5 kilowatt. How much each battery will supply? Let's say the one battery is the 1.5. Yeah, 1.2 kilowatt, other is the 0.7. If you have the different ratings batteries supplying to a common load, how much power each battery will give? Both are same. Depends on, so how to decide? What is the power sharing? Suppose my load is AC, battery is DC. You use the converter and then give. So that is called your droop at watch, the power sharing. So you have to, it depends. You can decide the controller. You want a battery which is of the say 0.7, give the complete power, and rest of the power you take from the other battery. So how to share power with the different sources, that you must be able to control. Like one will reach at the peak, but load is still required. How much the other sources will supply to that load? So that is a very important issue in nowadays microgrid. How the power sharing will take place. Dynamic load sharing in islanded mode, ensuring the power quality. Mostly your all power electronics engineer are working on this. So naturally all converter, inverter, that all you are using. What they are doing, as much as the power electronics are there, more and more harmonics will be there. And to improve your power quality, you require to reduce or eliminate these harmonics. And for again this, you require the controller, stability of the network and the transient in the disturbance period is another issue which is not completely addressed in microgrid case. Because depending upon what is the structure of your microgrid, the stability of the microgrid will depend. Because you have number of converters which are given in this microgrid, and as we have seen it, your states are keep on increasing and increasing. Integral controller everywhere you have to use. So it's very common the system will become unstable. So stability, again, the issue to be addressed. Seamless transition from grid connected mode to islanded mode. Suppose your system is working with the grid. Now your all references, all operation that are being referenced by the main grid. Suppose the grid fails and you have the islanded mode, your grid has to operate. What will happen? What kind of the solar system you have here in NIT? Solar again will work in the two ways. One is it is connected with the grid. Whenever grid fails, there is no supply, the inverter will get in the off mode. It can inject power when the grid is on. The another mode is your solar is supplying the power, grid is off, but solar keep on supplying the power. So whenever it is supplying with the grid, it take reference from the grid. Whenever the grid is off, then it has to take reference from some another point. Then only it can work, otherwise not. So this seamless transition from grid connected to the islanded mode, again, it's a very important issue. Even to detect whether your system is working in grid connected mode or islanded mode, itself is a research issue. Identification of the islanded mode, or when the system will go into the islanded mode, because you have to change all the operation. So first of all, you have to detect your system has reached into the islanded, and then the further control action, then you have to take. Optimize energy production from micro sources, this your planning issue, uninterrupted supply to critical load. Here will come your load management system. Capability of the black start in case of the grid failure. Like we say, the black start. Cold load pickup problem, which is also called this. Optimized operating cost of production and the power exchange with utility grid, which is when it is connected with the grid. So the control technique which is used in microgrid, that is the centralized, decentralized and distributed. In centralized, all data are gathered and calculated at a single point. Decentralized, each control unit only use the local measurement, no communication is required. And distributed, each subsystem may have own controller capable of information sharing with other controllers. So this is the distributed, this is centralized, and this is decentralized. Further, we can divide this as your primary control, secondary control, and tertiary control. In primary control, you use the inner loops. It is, you can say, the component level control. Secondary control is the restoration or synchronization, and tertiary control is normally whether to import power to the grid or take power from the grid. So whenever you're in the islanded mode, normally your primary and the secondary control will work. But once you are connected with the grid, then this tertiary control will also come into picture. Another we call the zero level control. Here, normally like the few properties of the devices is being used. Have you studied the LFC problem? Load frequency control. What happens in that case? How the frequencies of the grid is being controlled? Anybody can explain? By controlling the input power. So the change in the frequency is basically due to the electrical load. When the load is increasing, frequency is falling down. Load is increasing means there is an imbalance between the power generation and consumption. Generation is less than the load. So you have to increase the generation. So you are increasing the mechanical power. But mechanical power is increased by opening or closing the wall of your plant. But before that, you will open or close the wall. What happens? So the governor action will take place. It has an inherent property. So whenever there is a frequency will fall, it will increase the real power automatically. That is the property of the governor, which is called the free governor mode. So whenever a conventional plant I'm talking about is working, we ask whether it is in the free governor mode or the block governor mode. In the free governor mode, it's little bit support the frequency. Frequency which is to be fall down like this, it will fall down like this. It will fall and little bit improvement will come. That is the inherent property of your governor. Similarly, once you use the different converter, they will have their inherent property. So that is called your zero level inner control loop. So that is the way, this is the microgrid. Each microgrid is connected with the different sources, different type of the converters. Whenever you are controlling these converters, that is called your primary control. By use of the primary control, we support the change. Support the change means we support the control, but not completely eliminate it. We don't make what we call the steady state error zero, but still there is a steady state error by the primary control. But once we will use this, whatever be there, gap is there, we use the secondary level of the control, which will eliminate this steady state error. So what we are saying, inner loop, the group or centralized control, which we are saying are becoming my primary control part. Like the frequency which was without control fall down to, let's say, 49.3. With primary control, that is reaching to 49.7. But with the secondary control, now we are restoring it back to the 50 Hertz. That is by secondary control. So that is basically used by this secondary level of the control action. Here with the main grid, we are measuring PQ, PG and QG of generator, and by this basically using this PLL action, we are either drawing power from the grid or supplying power to the grid. So that is by tertiary control. So these three types of the control are commonly used in microgrid. And as we increase, my bandwidth decreases with the increase in control level. So grid feeding converter and the grid forming converter. Grid feeding converters are those which is used with which work in the grid connected mode. Operate as a current source inverter having high parallel output impedance capable of injecting real and reactive power to utility grid. in islanded mode adjust real and the reactive power given by PQ characteristics. Grid forming converter are those which work in the islanded mode. They are normally the voltage source inverter. This sets voltage and the frequency reference, utilize two regulating loop, outer voltage regulating loop and the inner control current regulating loop. Grid supporting converter, they operate in both grid connected as well as in islanded mode, includes both feature of the grid feeding and the grid forming converter. So like, I hope, like in NIT Kurukshetra, you are connected with the grid. So these are the grid feeding converters. So they will taking reference from the grid. So whenever the grid is off, they will stop injecting the power. In grid forming converters, they are the number of converters which are basically forming a grid separately. They are not used any connection with the main grid. They are generating their own and supplying to the load. And in grid supporting, so you have the inverter which is can work in CSI and VSI mode both. So here, whenever the grid is off, this converter is still feeding the load, depending upon what type of the selection you have made and what type of the control you are achieving. So in AC microgrid, your primary control in islanded mode and the grid connected mode without communication. With communication, this is nothing but the elaboration of the previous discussion. So, like we said, our main control objective is whenever we are working in the islanded mode. So without communication, we have the conventional droop and the improved droop application. Droop application we will see. With communication, we will have the concentrated control, means we are all in. Any question? So all information we are getting at one point. I think you, if you don't understand the meaning of anything that we can discuss. Master slave control method. There is a one converter will work as a master converter, other work as a slave converter. So all the references are generated by the master and all other converter has to follow the master controller. Instantaneous current sharing, angle droop control, distributed control method, 3C control, peak value based current sharing. So these are like we said how the different sources will share the power. We have taken the example. These are nothing but the method by which they will work. And that is when a proper communication is provided in the system. Means all the converter can interact with each other. So without communication, these are the droop control methods. For secondary control, we have the centralized approach, distributed approach, and the decentralized approach. Centralized approach, the each controller we are Previously, we already have discussed this. So this is our decentralized approach. Each control unit only uses the local measurement. No communication is required between the subsystem. And distributed, each subsystem may have its own controller capable of the information sharing with other controller. So you will have the each controller, but information is shared. In centralized, you will have the one controller, which is basically all information is with this central controller and which is controlling the each component. And here each component control is separate in the decentralized. So in secondary control, in distributed approach, we will use the multi-agent based technique, model predictive control, consensus based control technique, decomposition, average of the PI control, finite time control, non-linear distributed control. So whatever I'm giving, that all methods are available in literature. So that are the common techniques which are normally used. So if you will see this distributed approach, it's not a new technique. If we just study the control structures that are taken from the control literature, not from the microgrid literature. How we use the control of the any device, how we implement the controller. Suppose a motor control you have to use, how you will use it? Once you are in an industry, in the laboratory, that's fine. Machine for PhD work, data you have to take, you can do this. In industry, how we use the controller? There's a number of machines are there. There you use the centralized controller. So you basically place the sensors and all these sensors are sending data to the one common operator. He's sitting and seeing the, say, what is the speed of motor 1, 2, 3, 4, 5. And accordingly, all control action he is taking by sitting in a control room. Even power system, how the controller control action is implemented. So for each, you will have the control centers, from where you are getting the information of the different buses at that particular point. And from that room, you are simply implementing, because they all are assisted with the communication network. In laboratory, once we will perform the control application, I think you all will done that. The DC motor speed control, armature control, field control. So you will have your armature resistance, field resistance, controlling, and each component you are controlling by separately. That is your decentralized control. Centralized control, I'm sitting here, I'm getting information from my all the machines. All data is available with me. Now I know which controller I have to operate. So the operator is taking the decision. So that is the difference here. So in the distributed approach, now these are the techniques which are normally utilized. And the same technique we are also implementing in the microgrid. Tertiary control, is the global control. It's mainly act when the microgrid operated, grid connected mode remain inactive in islanded mode of operation. Similarly, for DC microgrid, Shyam, what is the time limit? Ten 15 minutes. 4:30 try to finish. So this is the primary control approach, secondary control approach in the DC microgrid control. In case of the AC microgrid control, there are the two parameters which are mainly to be controlled, that are the voltage and frequency. In DC, we normally have the voltage to be controlled. So conventional droop, improved droop, which is your virtual resistance, adaptive droop control, intelligent technique, mode adaptive droop control. What is the droop? We will discuss just now. With communication, we have the centralized control, and similarly, for secondary control, we have the distributed approach with these four type of the controller. So very quickly, I will discuss. These are only the theoretical part. Leave it. The first application for the control, we will take the MPPT. As all you know, this is the PV curve of the solar panel. As your so the x-axis is your voltage, y-axis is your power. So this is the with voltage, the output power will change like this. This is the IV characteristic, current and the voltage characteristic. And the power, as we know, this is nothing but the product of the voltage and the current. If I will multiply I and V at this point, so that will be my power will be 0. So that's why we are saying the power is increasing, reach to a maximum, and then it start dropping. So in MPPT application, my objective is to track the power. So my panel will operate at this point where it is supplying the maximum power. But at this power, you can see its voltage is less than what you call the VOC voltage. So that is called your operating voltage under maximum power condition. So basic approach here is, which you call the P&O approach, perturb and observe. You change the voltage, check the power. If it is in each step, when it is positive, it start changing the voltage. Once it will reach to this point, del PV by del V will become 0 because it's going to be flat, and then this will become negative. So in the perturb and the observe, we will select this particular point to track it. And how we will track this? Say what we can in a solar, we have taken the PV panel, which is giving you the output voltage. This is your DC-DC converter, giving you the constant voltage, and then your battery and the resistive load, something you have connected. My objective here is this will work. This we call the MPPT converter. So how we are basically setting this voltage? by changing the duty cycle or by making the operation of this DC-DC converter. So we will try to set with this P&O algorithm so that this will work at the VMPP. We set that voltage which is giving me the maximum power. So by this my MPPT controller will work. But once you will have the different partial shading condition, whether you have the number of panels, the few panels will have the shade, few panels are open. So their solar irradiation is changing on each panel. So in that case, you will get a curve like this. So in this case, your P&O algorithm will not work. If I will see, this is my point where it has to operate. But what will happen in P&O approach, we will start from here, move, and whenever this point will come, we will take this as my maximum power point. So this will give me the local minimum, not the global minimum. So here the modified P&O approach is given. So what we are doing, the overall, we are dividing into the different number of the zones. And in each zones, we will try to get the maximum power. And in the zone where is the maximum power, that particular duty cycle is selected for that given maximum power. I hope you are following me. What we have done, like here we have divided, take the 1, 2, 3, 4. 4 level we have taken. In all the 4 levels, we are calculating the voltage and the power. And said you can have the maximum power here, maximum power here. So here you will get the maximum power in the first P&O case. I'm getting my maximum power. But if my condition is like this, I will hang up on this. If I will get the maximum power in this zone, in all the 4 zones, I know in which zone my power is maximum. Like in this case, I know my power is maximum in this zone, next zone. So I will set my duty cycle as per this maximum power in place of this maximum power. So that is the change in the partial shading condition of this P&O approach. This is simply the application by which this is implemented. So that is the work of my one student who has basically done this and implemented this controller. So this is our tracker is basically selecting this as my, in the third condition, the maximum power it is selected, where the conventional is failed in the third case, which is of this. So these 3 scenarios are checked. So first 2 scenario, both the controller works, but in the third scenario, our proposed controller will qualify while the conventional P&O controller will fail. And basically to track this, we use the P&O approach. Even here we are using the P&O. To calculate power in each zone, we are using the P&O approach. But that maximum power for each zone is calculated separately. So this is planning issue, I'm just leaving just for your understanding. And the application of the primary and secondary. This is another work which I am discussing, that is the interlinking converter operation in hybrid microgrid. First of all, you take this system. Here we will have, you can say this is my DC source. DC source means here I will have the renewable source. You can take it as a solar, fuel cell, any type of the source. Similarly, here we will have the renewable source, but here we will have the AC bus. So we have the DC bus, AC bus, both are basically connected with a interlinking converter. So objective here is to get the operation of this system, which is nothing but a hybrid microgrid, which will have the DC load as well as the AC load. Here, this load may be more than this load, then this side, this power is supplied to DC side. Suppose DC power is more and AC load is, AC power is less, so the power can also be transferred from this side. So in this case, once we will have the AC side, then our objective is to control the voltage as well as the frequency of the AC bus. While on DC side, our objective is to control the voltage of the DC bus. And the interlinking converter can supply the power in both sides, depending upon your load scenario. So this is basically our condition. So objective is to study the interlinking converter operation in hybrid microgrid. Hierarchical control, primary and the secondary control is implemented. In primary control, P by F group and the QV group is used in AC section. PDC, VDC group is used for the DC section, and the hybrid group as along with the low pass filter is used in interlinking section. In secondary control, restoration of the VAC and F in AC section and the restoration of the VDC in DC section is achieved. So DC to AC converter, we have the V by F group, means when the real power increases, the frequency will fall down. And Kp here is the slope of this line. So what will be the frequency? That will be the F0 minus Kp PAC minus P0 AC. P0 AC is this, and the PAC is at any point if I'm getting. So by this we will define the droop. Similarly, this is the QV droop. Q represent here the reactive power, P for the real power. As we know, frequency is dropped due to the real power and voltage is dropped due to the reactive power. Here this is the KQ and the VAC. By the simple equation we can decide by this. Is it fine? So this is used for the primary control. Similarly, we define the DC-DC converter, only the voltage group will come because there is no frequency is on DC side. And similarly, the VDC can be V0 DC minus KDC, PDC minus P0 DC. And this is your hybrid group. So to control the loop, consist a current controller is implemented in the synchronous reference frame, and the current reference is defined using the hybrid rule. This is for your DC, this is for your AC. And the PIC is the P naught, KAC, IC, F minus F naught, KDC, VDC minus V naught. For further improvement on the real power transfer, low pass filter is used. The use of LPF affects the dynamics of the interlinking converter. The sudden change in load on DC bus or AC bus is smoothly controlling the power from the other side and maintaining the per unit power balance is equal to this value. In secondary control, our objective is to eliminate that error. So delta F is defined by this equation, delta VAC. So these two will restore the voltage and the frequency on the AC side, and this will restore the frequency on the DC side. Sorry, restore the voltage on the DC side. And this whole is our system. These are the system parameters. This is the controller on DC-DC converter. So this is my DC-DC converter. So that is your P naught DC and the V naught DC. They are the two references. And this is my VDC. What is my VDC? This is my VDC. So it is basically nothing but setting the reference for my DC side. And similarly, these two will set up the reference for frequency and for AC side. So by this, you can implement this controller. So in AC side, we will have the two control loop. Where the VDC is here. So this inverter control we are getting by using the DQ reference frame. So this is the voltage control loop and this is the current control loop. This is your secondary controller and this is your primary controller. So that is generating your delta F to control the frequency. And this is for your interlinking converter loop. The control which is implemented. And by the result, we can show that the three cases are taken, the real power plot, AC bus, when restoration are not performed and the load change from T1 and T2 in the AC and DC case. So you can see from here, the frequency in case of the AC is not restoring. Similarly, the voltage is also not restored. And there the power flow which is given. Scenario B, the restoration of the AC bus frequency and the DC link voltage. So this is your I think this is for your frequency, which is returning back to the 50 Hertz. So it is restoring the frequency after secondary control. And here it is maintaining the DC voltage in DC case. And this is showing the change in the load. In the first case, when load is changing, the frequency is falling. So because load keep on changing, frequency is maintaining. So that is your called the zero level, which is still bit try to maintain the frequency, but the frequency is falling down. Similarly, the DC voltage is falling down. So that is the effect of the primary control. While in the secondary control, they are trying to restore the voltage and the frequency both. Now this shows the power from AC to DC and DC to AC, interlinking power scenario, which is simulated here. And there are the few standards which are emerging, and the IEEE standard committee is still working on this, which are followed in the microgrid. So here I will rest myself. So, any question that you can discuss?
Yes. Now I will open conference. You may ask some question.
In AC microgrid, you said that we have to put high voltages to DC. And how much it should be? And there is no any standard.
There is no standard. That will depend upon how long you have to supply the power. Say if like in this room you have to supply, so depending upon your equipment, you can decide.
You said that the project is in IIT.
Say like in which we have developed in the laboratory, that is a 120 volt. So 120 volt DC bus we have, and whenever we require the different loads, accordingly we convert them up to that voltage level. In Dayalbagh, Agra, where we will have the line, we have the two DC line there. One is at the 48 volt, which is directly connected to the lightning. And the other is the 360 volt, which again gone to little bit near about 500 to 1 kilometer. And there at the required level, again using the small converters, they have been converted at the required level.
Also use 1,000 volt.
It say basically as you increase the voltage, the dangerous level that safety standard you have to check. Because the DC at very high voltage will become very dangerous. The HVDC is a different thing. HVDC, once you have to transmit.
LVDC, low voltage.
A low voltage DC is normally above, I think, 96 volt. It is considered to be the threat on the life if you are directly touching this. So whenever you are using the DC wire, so that's why we say how long you have to transmit the DC. That will become important. Because the 48 volt you have to go for the 500 meter. That is a quite long distance. So you have to transmit. So through the cable, higher cable you can transfer. So there is no issue of capacitance, or capacitance may be there, but the inductance issue is not there. Working? Work is still on? कुछ करिए, कुछ नया नया निकालिए आप लोग.
Okay, anyone? Yes.
Yeah.
Sir, when you were seeing that when the solar source, solar PV was supplying power, and then the load increased, high voltage was experienced. I thought that the controller is okay to control the output voltage. So how come when the load goes down, the controller is able to control the voltage and still experience high voltage in the load and destroy the line in the battery?
See, controller, like we said, in solar case, we will have, if we are using the AC voltage. So the DC, the boost converter voltage is being controlled, which is the input to your inverter. So inverter is giving you a certain voltage. Naturally, this voltage will depend upon how much power you are supplying. If it is directly feeding with this and the load is being reduced, as the load will fall down, your voltage keep on increasing. So controller will try to compensate that voltage. So what you are doing, I have the voltage transmission line, and here I am basically feeding the power. So when the load is reducing, here is its overall voltage is increasing. Now you are feeding more power from the solar side. So this will give the boost to the voltage. Same like you will have in the Frente effect. Your load is being reduced and voltage is increasing. So that voltage will increase at your terminal point. The voltage which you are receiving at this computer terminal input. So the other load will reduce. So this terminal voltage will rise. It's a normal phenomenon. Once my overall system is working, let's say 100 kilowatt, and suddenly your load will reduce to the 10 kilowatt. So what will be the effect on the voltage? But in this 10 kilowatt also, your solar is connected. So these are two different sources, because the solar power is not controlled by the load. Your another generator power is controlled. So this is going rise to the voltage. The same Frente condition is appearing. That's why your voltage will increase.
So, sir has discussed about every microgrid actually. The first part had discussed about AC microgrid, or we can say conventional grid, and later sir has covered DC microgrid, as well as sir have discussed one work that means on hybrid microgrid. Yes, in hybrid microgrid, DC voltage are regulated, as well as AC side voltage and frequency control, active and reactive power with the help of loop control, like that. As well as sir discuss about all types of controller scheme of the microgrid. In that way, we can say sir has covered rightly, and thank you sir for this wonderful lecture. So welcome all participants who have put up nice question. So thank you to everyone. Thank you, sir.
Thank you. Thank you giving me the opportunity. And the patient hearing, which we got.
Yes, sir.
It's not easy to sit 2 hours.